Okay, so I'm going to talk about geodesic completeness of compact Lorentzian manifolds with special holonomy, and I added this to the title. I guess I just forgot it in the original title, but of course I'm talking about specific special manifolds and not in general about every compact Lorentzian manifold. So this is joint work with Daniel Schliebner, who was at Humboldt University. Unfortunately, is no longer there. It's not a very new result, so it's a couple of years old. But I think it's interesting, and I think it fits very well in this meeting. And I have some open questions, interesting open questions that I really would like to answer. And that's why I just thought it's a good idea to talk about this at this conference. I think some of you have seen a similar talk before, so I apologize for that. Okay, so this is about geodesic completeness. Can everyone still hear me? Is everything okay? It's very...
Everything is okay.
Okay, good. Okay, so this is about geodesic completeness. So we start with a semi-Riemannian manifold, have Levi-Civita connection. We can define geodesics as solutions to this ODE here. And in coordinates, you can write the geodesic equation. And we know from, since these are ODEs, we know from the theory of ODEs that there's a maximal solution. And this is defined on an interval or possibly on all of R. And it's unique if we specify these two initial conditions. So it's a second order ODE, and we have to specify these two initial conditions. And I think I'm just realizing that my slides are a little bit too introductory for the audience, but I guess I'll just keep going and explain everything from the very beginning. And we say that the manifold is geodesically complete if this maximal interval for each geodesic is just all of the real numbers. So this must hold for all maximal geodesics. And of course, if MG is Riemannian, then we get the manifold becomes a metric space. So we can define the length of a curve. And so the manifold becomes a metric space with this distance function. So we just take the infimum over the curve length between 2 points. And the well-known Hopf-Reno theorem tells us that this metric space is complete if and only if the manifold is geodesically complete. So that's why in Riemannian geometry, it makes perfectly sense just to talk about completeness and not about geodesic completeness. However, in pseudo-Riemannian context, this metric space, we can't really define this metric space in this way. And so because of the Hopf-Reno theorem, and because we know that every compact metric space is complete, we get the following theorem, which is very fundamental in Riemannian geometry. Compact Riemannian manifolds are geodesically complete. So if you have a compact Riemannian manifold, you don't have to analyze these ODEs at all, because you know that their interval on which they are defined is always equal to R. And this theorem can be proved directly. You don't need the Hopf-Reno theorem for it. I mean, the Hopf-Reno theorem is very heavy machinery to prove this result. And so let me briefly explain you how to prove that. And the proof will also show why it fails in the indefinite context for indefinite metrics. Okay, let me just go to the next slide. So this proof sort of is based on the geodesic flow that we can define on the tangent bundle of a manifold. So we define the geodesic vector field X on Tm in the following way. So we take a point and a vector in Tm. V is a tangent vector at the point P. And then we define the following vector field. So we take the geodesic with initial conditions P and V, and we differentiate this at the point T, at T equals to 0. This gives a tangent vector to the tangent bundle at this point PV. And this definition just defines a vector field on the tangent bundle. And this is, so this what is in these brackets here, gamma T, gamma dot of T is called the geodesic flow. It's the flow of this vector field. So if gamma now is a geodesic, it has constant length. And in the Riemannian case, it has positive constant length. This means that gamma dot of T is contained in the sphere of radius r. Yeah, so this is the sphere in the tangent space at gamma of T. So this means that the integral curves of this geodesic vector field remain in the sphere bundle which is the subbundle of the tangent bundle. But the sphere bundle is compact if the manifold is compact. And now we know that integral curves of vector fields are defined on R if they do not leave a compact set. So that's why we get that the integral curves of this vector field X are defined on R, and hence the maximal interval for this geodesic is also equal to R. So this proves the completeness of compact Riemannian manifolds without using Hopf-Reno. And we also see why this fails for indefinite metric, because for indefinite metrics, the level sets of the scalar product of the metric are not spheres anymore, they are non-compact sets. So for example, if our metric is Lorentzian, then this quadric here, this level set, is either the zeta space or hyperbolic space or the light cone. So in each cases, this is the non-compact set, as opposed to the Riemannian setting where we just have a compact sphere. So even though the length of the velocity of the geodesic remain constant, it can still move around the velocity can still move around in a non-compact set, like here or here. Right? So this causes problems when trying to do this proof, because the velocity does not remain in a compact set. And indeed, there's a very elementary example of a non-compact, complete compact Lorentzian manifolds. That's the Clifton-Pohl torus. So let me just briefly explain that to you. So we take the manifold M tilde, which is R2 minus the origin, and we define the following Lorentzian metric. So this metric here, so the directions du and dv are null directions in this case, and we rescale by this function. So it's a conformally flat metric. And we can just write down the geodesic equation. It looks like this. And then we can see that the solutions, for example, for these initial conditions, so we start at the point 1, 0, and the velocity is given as d over du, that the curves, the geodesics with these initial conditions are given like so. And they have a singularity. So if t is equal goes to 1, this goes to infinity. Yeah? Although the length of the velocity is 0. So this is a light-like geodesic. So this is still not compact. That's just R2 without the origin, but we can compactify this by forming a quotient. So we take the following map, which is a homothéty of the Euclidean metric, but it is also an isometry of this Lorentzian metric up here, because we rescale in the same way as we rescale the coordinates. So this is an isometry of this incomplete metric. And if we take the quotient, we get the torus and the 2 torus. So we have an incomplete Lorentzian metric on the 2 torus. Because if the metric on the cover is incomplete, also the metric on the quotient is incomplete. And this can also be generalized to higher dimensions. So here's a formula for some similar phenomenon in higher dimensions, where we just added some space-like direction, and it still remains an incomplete metric on a higher dimensional torus. And I mean, in this example, the incomplete geodesic was light-like, but one can also construct incomplete examples where there's space-like incompleteness. So the fact that this geodesic is light-like doesn't really matter in this example. Okay. Yes, so let me see what's happening here. Yes, so I'll just continue. Just a few comments and a few words about motivation, why one would study geodesic completeness. So first of all, these examples, they show that the sort of very naive intuition that incompleteness corresponds to points missing from the manifold fails in the Lorentzian context, right? Because a compact manifold is not missing any points, but still it can be incomplete. And really the crucial thing is that the velocity vector does not remain in a compact set, even though the geodesic does remain in a compact set. So maybe for the Clifton pole torus, I should say that these incomplete geodesics on the compact set, they're just running around this torus, getting faster and faster, but still their length is of the velocity is 0. So why should one be interested in geodesic completeness? This is because of the following fact that I've already used in the example. If you have an isometric covering, then the quotient or the base manifold is complete if and only if the cover is complete. So this leads to the following argument. So if we have, for example, a compact manifold with some curvature condition, for example, a flat manifold, constant curvature, or locally symmetric, and this manifold happens to be geodesically complete, then M is covered by a model space, a geodesically complete model space. And this would be a simply connected complete manifold with this curvature condition. So for example, spaces of constant curvature, we would have de Sitter and anti-de Sitter, etc. So this means if you want to try, for example, to try to classify certain compact Lorentzian manifolds, you can reduce this, after you've shown that they are compact, you can reduce this to the question of classifying groups that act properly discontinuous on the model space. And I mean, this is still a very difficult question, obviously, but at least you can sort of transform the problem into some algebraic problem. So let me show you a big table that sort of illustrates this idea a little bit. So let's look at, for example, Riemannian model spaces, right? So we have flat Rn, obviously, then we have the sphere and hyperbolic space. And then we have, if you look at locally symmetric spaces, we have the irreducible symmetric spaces. So G is a simple Lie group and H is just a maximal compact subgroup. And this would give us all irreducible symmetric spaces in Riemannian signature. In Lorentzian signature, the picture is kind of similar. So we have also flat and constant curvature. So we have de Sitter and anti-de Sitter. And then the indecomposable locally symmetric spaces, there's just one class, and these are the so-called Kahn-Baller spaces. I will come back to this and I will explain them a little bit further, and I will also say what I mean by indecomposable. So the message that I would want to tell you here is that in the Riemannian setting, there's a long list of irreducible symmetric spaces, whereas in the Lorentzian setting, there's just these Kahn-Baller spaces, apart from constant curvature, obviously. Okay, so what happens now in the Riemannian setting? If you have compact Riemannian manifold, it is complete. And hence, for example, compact flat manifolds are just classified by the Bieberbach theorem. So they're just given by Rn modulo gamma, where gamma is one of the Bieberbach groups. So it's essentially given by translations. So the next, if you look at compact quotient of the sphere, they were studied by Joe Wolf. And of course, in the hyperbolic setting, this is the whole world of hyperbolic geometry. And that's why I guess I was lying a little bit when I said classification, but at least it leads into a specific sort of area of problems. And for symmetric spaces, this is similarly complicated, these Clifford-Klein forms. But one can study these groups that act with compact quotients, compact manifold quotients. Okay, so let's go to the Lorentzian situation. So if we have a compact Lorentzian manifold, we can ask the question, is it complete in these sort of model space cases, right? So in the flat case, this was proven by Carrier in 89. And this leads to a similar argument. You can now try to classify these groups that act co-compactly on Minkowski space, and Goldman and Kamishima have shown that these groups have to be polycyclic. In the constant curvature case, the completeness of compact manifolds was proven by Klingler in 96. And then in the next step, Calabi and Marcus showed there are no compact quotient of de Sitter space. Well, I guess they showed this before Klingler's result. And Kulkarni has shown that only odd-dimensional quotients of de Sitter space, only odd-dimensional de Sitter space can have compact quotients. Yeah, so this kind of, but the completeness is used in order to conclude that these are all compact manifolds with constant curvature. And so this is where sort of our result fits in, because as a consequence of our result, which I will explain in a minute, is that compact Lorentzian manifolds that are locally symmetric or locally Kahn-Walla spaces are complete. So hence, these compact manifolds are given by quotients by the standard Kahn-Walla space by a lattice in the oscillator group. And this was studied by Cart and Olbrich, these co-compact, so these lattices in the oscillator group that give compact quotients of Kahn-Walla space. Okay, so this is kind of a bit, I guess, an outlook and still motivation of the problem, why completeness is important, in my opinion. So let me just briefly recapitulate the results that there exist about completeness of compact Lorentzian manifolds. So the first result goes back to Marston. He showed that we have a homogeneous pseudo-Riemannian manifold, like globally homogeneous and compact, then it is complete. The next result that is very important is Carrier's result. So he proved a much stronger result. He proved the Marcus conjecture about flat affine manifolds. And then the next result was by Kamishima. I mean, since Carrier's result, one wanted to generalize this to constant sectional curvature, but Kamishima needed this extra condition of the existence of a global time-like Killing vector field. Then Romero and Miguel Sanchez proved a much stronger result where they only assumed the existence of a time-like conformal vector field. And that's actually a very nice paper, also a very short paper, because the proof fits on the first page. So there's the title, then there's the abstract, and then there's half a page of proof, which is a really ingenious proof, in my opinion, because they just show that the projection onto the line spanned by the Killing vector field is bounded, and hence gamma prime has to remain in a compact set. And this is what I showed you at the beginning is enough to show completeness. And then the constant curvature case was finally proven by Klingler. And so he uses similar method as Carrier. So he uses GX structures and the development map on the map model space. And he used that to show that the universal cover is complete. So these are very difficult proofs. I currently have a master student who's trying to understand them, and he's working very hard. Yeah, I hope he will succeed. And then there's another result by Dumitrescu and Garni-Segib, where they looked at the local situation when you have locally homogeneous instead of globally homogeneous. And in dimension 3, they could show that locally homogeneous dimension 3 compact implies completeness. And our result is about these so-called PP waves, compact PP waves, and consequently the locally symmetric spaces are complete if they are compact. Okay, so now I'm going to explain what these PP waves are. And clearly in the compact setting, there's a bit of a misnomer, but yeah, so we just have chosen to keep this name PP waves as it was established in the literature. So let me start by explaining a little bit about Lorentzian manifolds with a parallel null vector field. So we have a Lorentzian manifold with a vector field that is covariantly constant. So nabla v is equal to 0 and is also null or light-like, if you prefer. And so v is invariant under parallel transport. And the tangent bundle is filtered into parallel subbundles. So there's this line bundle spanned by this vector field. Then there's L orthogonal, which contains the line, which is codimension 1 in the tangent bundle. And all these distributions are parallel, invariant under parallel transport, and hence integrable. And so they yield a foliation, in particular the one of L perp yields a foliation of M into hypersurfaces. And one can then define what is called the screen bundle, where you just take L perp mod L. And on this bundle, you get a positive definite metric by this formula here, which is well defined because V is a null vector field. And you also can define a connection on this bundle. And again, this is well defined because the vector field is parallel. So this is a vector bundle with a positive definite metric and a compatible connection. And this will play an important role in our definition of the screen bundle. And the screen bundle is sort of invariantly defined, but you can identify it with what is called a screen distribution. This is just a subbundle of the tangent bundle that is given by L perp modulus intersected with Z perp. And Z is a vector field that is a null vector field that is transversal to the distribution spanned by V perp. So we will come back to the screen distribution later. So let me just use the screen bundle now to define what a PP wave is, and then sort of look at more familiar definitions of a PP wave. So we call it Lorentzian manifold PP wave if it admits a parallel null vector field and the screen bundle is flat. The screen bundle with this connection that I've just introduced, which essentially comes from the Levi-Civita connections. So this is what I call a PP wave, where the screen bundle is flat and we have a parallel null vector field. So there are equivalent descriptions. So you always need the existence of the parallel null vector field, but after that you can find other definitions or other equivalent description. One of them is that the curvature tensor has the following property. So if you put in two vectors into the curvature tensor, you get an endomorphism, and this endomorphism maps V perp into V. Yeah, so it contracts, the curvature is very degenerate, it contracts codimension 1 subspace into a line. And here's perhaps the more familiar definition in local coordinates. So if you have this definition of a PP wave, this is equivalent to locally having these type of coordinates. So the metric depends just on one function on the u and the xi coordinates. So the dimension of the manifold in this example is now, or this formula is n+2, which is more convenient instead of being n. And so the metric depends on one function on this, just on one function on all but one variable. And here this is just the Euclidean metric. Okay, so if we have this metric and we have it defined on all of Rn, we call this a standard PP wave, just for short. And you can easily see what the screen distribution is. It would just be spanned by these d over dxi's. And one can also compute the curvature of this, and it's just given by the Laplacian of this function h with respect to these to the space-like coordinates xi, x1 up to x2. So this means if h is harmonic with respect to the x coordinates, you get a Ricci flat metric. And of course, one can also write down easily compact examples of PP waves where you just imitate this local form of the metric, but just put it on the torus. So you have this form of the metric here, and this gives you easily compact examples. And as I said, the name wave is sort of a bit a misnomer for compact manifolds, but it is established in the literature, and so we just use it also for compact versions. Okay, so why would one study PP waves? So I mean, it's a very special condition, so I feel I need to motivate this a little bit, why one would look at these. So they were kind of invented or discovered, if you want to say, by Brinkmann in 25, in a completely sort of surprising context, namely in conformal geometry. So he looked at the question, when can an Einstein metric be rescaled to another Einstein metric, conformally rescaled? And this happens in two cases. So either when the manifold is a product of a space of constant curvature and R, so a warp product. This is when the gradient of the scaling function is has non-zero length, or it is a PP wave metric in dimension 4. So this was all in dimension 4. So this is really where this local form of the metric popped up essentially out of nowhere in conformal geometry. And then, of course, there are the more familiar examples of PP waves as wave-like solution to the vacuum Einstein equations. So this is what I just explained with the function h being harmonic. And so this is also, I guess, where the name comes from, because these VU constant submanifolds carry a flat Riemannian metric. And then they were also mentioned in Elast and Kun, and they called them plane fronted with parallel rays. I think this is where the two P's stand, what the two P's stand for. And they posed this following problem, which already has completeness in the formulation. So prove that complete Ricci flat PP waves are plane waves, no matter which topology one chooses. So I will come back to this later, what plane waves are, and our sort of partial answer to this question. So Penrose found out that every space-time has a plane wave limit. So this is a well-known Penrose limit. They're also important in supergravity because they carry lots and lots of parallel spinners. So not the maximal number, but the sub-maximal number of parallel spinners. And an interesting feature of these PP waves is that they have no scalar invariance. So if you want to find a function that is coordinate independent, it's impossible. So that is given by derivatives of the metric, obviously. So they have no scalar invariance. So every trace you form from the curvature tensor, its derivatives and all sorts of control, they will all vanish. So this was proven. Strictly proven, but I can't remember who did this. And so my interest comes more from holonomy theory, because they have what is called special Lorentzian holonomy. They have abelian holonomy Rn. And another interest is that these indecomposable Lorentzian symmetric spaces that don't have constant curvature are special forms of PP waves. So that's why these two things were the reason why I started studying them. Okay, so I think I'm halfway through my talk, so I should present you the main results. So here's the first. So we were trying to answer the question, when is a compact PP wave geodesically complete, or is it always geodesically complete? And first we looked at the universal cover of a compact PP wave, and we were able to show that a compact PP wave is isometrically covered by a standard PP wave. So here's again the formula for a standard PP wave. And not only that, very important, we could also show that these functions, the second derivatives, so essentially the Hessian of this function h with respect to the xi coordinates, that these are bounded functions. And this is very important when you look at the question of completeness. So now we know what the universal cover of a compact PP wave, what it looks like. So then you may ask, is a standard PP wave geodesically complete? And you just can write down the geodesic equation for this metric here, and they are not very difficult. So for example, the u coordinate, you just get an affine function. The v coordinate, so you see that the right hand side does not depend on v, so you can just integrate this. So everything depends on the x component of the xi component of the geodesic. So if this is defined on R, then the second solution is defined on R, and so it really depends on this third equation here, which has the gradient of the function h on the right hand side. So in general, these are not complete, because we can just easily write down an example. So for example, if h is 1/2 x to the power 4, I don't know why I put this 1/2 there, but I think it simplifies things a bit. So then the geodesic, this third equation just becomes this equation here. And if you solve it, you see that you get a similar phenomenon as for the Clifton pole torus. So there is a singularity. So that's why this condition here, that if the standard PP wave is a cover of a compact PP wave, that these functions are bounded. So this is important to show that they're actually complete. Yeah? So we have shown in the first theorem that these functions, the second derivatives, are bounded. So this shows that a compact PP wave is actually geodesically complete, because the boundedness of the Hessian implies that the universal cover is geodesically complete. So these are the two main results that we have obtained. So I will talk about some applications in a minute, Let me just tell you briefly how the proof goes. I hope everyone is still there. There's nothing in the chat, so I guess I just continue.
Yes, we are here.
Well, I'm a bit traumatized because I once saw a talk where someone gave his talk, but he wasn't there anymore. And he returned after half an hour. He came back and he said he had just given his talk to no one, right? So I'm a bit scared that this happens to me as well. Right? This person was very angry, but yeah. So that's why I keep on asking every now and then if everyone is still there, so that I don't talk into empty space. Okay, so let me just. Yeah, sorry about this.
No.
So I just continue with sort of giving the basic ideas of the proof. I can't give the details, obviously, but I will sort of boil it down to two sort of black boxes, let's say, that I can't prove. So the basic idea is as follows. So you look at the universal cover of this manifold, and you get a one-form eta, which is just the dual to V, right? So this is a one form, a globally defined one form, and because M is compact and because it has a parallel global vector field, it is time orientable. So you can actually you get this global vector field defined Z called Z such that eta of Z is equal to 1. And because M is compact, this vector field is complete. Moreover, because V is parallel, this one form is closed. So once you have a closed one form and your manifold is simply connected, which happens for the universal cover, of course, you are kind of in business, because then you can know that the kernel of this one form is an integrable distribution. So then you know that the universal cover splits as a product the universal cover of a leaf times R. So in some sense, you have sort of already won the first R direction that you need, right? And this map can be explicitly described by the flow of this vector field, right? So that's good. So that's a start. But then you may think you are stuck now. But then for a PP wave, the screen bundle is flat, right? And if you work out what this means in terms of geometry of the manifold, you can show that each leaf of this distribution V perp, so it carries the induced connection from the Levi-Civita connection, because these are totally geodesic. It's a totally geodesic foliation. So you got this connection on these leaves, and because of the flatness of the screen bundle, this connection is also flat, right? So now you have a flat manifold with a flat connection. Universal cover is simply connected. So what you do get is a global frame of parallel vector fields on this leaf. Yeah. So and of course, the first parallel vector field is the lift of your parallel vector field V that you started with, and then you have these SIs, right? Okay, so the problem is that these vector fields may not be complete, right? So if we could choose these nabla tilde parallel vector fields to be complete, then we could just apply an old result of Palais to get that n tilde is also Rn plus 1. So what is this result? So he proved that if you have a complete frame field such that the Lie brackets of these vector fields has constant structure constant. So I mean, these are functions that are, so these are constants. So the commutator of xi and xj is constant times xk. Then M has a unique Lie group structure such that these xi are left invariant vector fields. And of course, in our case, provided we had complete vector fields, these are parallel, all these constants would be 0. So the unique Lie group structure would be just those of Rn plus 2, right? So the question, I mean, this looks kind of simple, but the problem is to get these complete vector fields with respect to this induced connection. So, okay, so now, so this is kind of a bit of a dead end, but it gives some ideas what you need to do, perhaps. So you have to kind of get the completeness somehow, these partial completeness. So this is where these screen distributions become important, because they define Riemannian metrics or auxiliary Riemannian metrics. So we can fix a null vector field that is transversal to V perp, and then we can identify the screen bundle with the tangent subbundle, which we call the screen distribution. So you just take V-perp, intersect it with Z-perp, and that's a codimension 2 distribution in the tangent bundle. And you can use this to define a Riemannian metric on M. So you just change, so on S, you just take the Lorentzian metric because it's positive definite on S, and then you make V and Z just unit vectors, and they're orthogonal to the screen. So this gives you a Riemannian metric, and because it is on a compact manifold, it is a complete metric. So we have a complete Riemannian metric, but of course, its geodesics are different from those of the Lorentzian metric. And these leaves these hypersurface leaves are totally geodesic for this metric. Yeah, so this is what I just said. H is complete because M is compact, and then you can show that the induced metric on these leaves, even though the leaves may not be compact, but it's still compact, it's still complete, and we then lift to the universal cover. So now we have complete vector fields because these SIs, they are geodesics vector field, but the metric is not flat, right? So this is a problem. If this metric H induced by the screen was flat, then we would have a global frame of complete parallel vector fields. So again, we could conclude that n tilde is equal to Rn plus 1. However, this metric in general is not flat, and it is flat if and only if the screen distribution satisfies two properties. It is what we call horizontal and involutive. So involutive is just the usual condition, of being integrable. And horizontal is just this condition. If you commute V with the section from S, you are back in S. Right? And locally, these conditions are trivial, as you can see from the local coordinate description of the PP wave. But globally, they are non-trivial. So in particular, there are examples of compact PP waves which do not have global screen distribution that are horizontal and involutive. So yeah, so that's why it's not that easy. So in print, I mean, what you're trying to do is to mimic the local situation in the global context, but you run into some difficulties. Okay, so so these are sort of two lines of approach, and you just need to combine them somehow to get the result. So we can start with the given screen, which is just an arbitrary screen distribution, lifted to the universal cover. And since this is not necessarily flat, or the metric induced is not necessarily flat, we get sections of the screen bundle that satisfy this condition. These are global sections, but they're not parallel, right? So they are sort of the covariant derivative lengths in the V direction. So they are geodesic and hence are complete, but they're not parallel. Well, on the other hand, one can show, and this is kind of one of the lemmas in our paper, that on a simply connected manifold, so on the universal cover of M of our PP wave, you can always find a horizontal and involutive screen distribution. So not on the manifold itself. So the original one comes from the base manifold and you lift it, but it doesn't have the good properties. But on the cover, you can then change it. And these sections are then related. So they differ by a function times this vector field V. So that these SI are complete, these other ones are parallel. So what you need to show is that this implies, this is the first black box kind of claim, that these SIs are complete because the SI and the SI heads are complete because SI and V tilde are complete. And again, then so if we prove this claim, and which we did prove this claim, then this is again, the leaf is again equal to Rn plus 1. So this shows that the cover is given by Rn plus 2. Yeah. And so this is this claim. I can't really explain how this goes because it's a bit technical. Then you still need to show what the lifted metric is. Yeah. So this is also a bit technical. This is my second claim. This uses Jacobi vector fields, right? So, and then the last lemma is to show the boundedness of these second derivatives. And what we did here is, so we defined a bilinear form on the base manifold, which is compact, where we just take the curvature, put in the screen vector field, so saturate the curvature tensor in 2 entries, and get a bilinear form, symmetric bilinear form. We can look at its length in some sense, so apply G to it. That's a function on the compact manifold, hence it's bounded. It's also positive definite, but it's bounded. And then you just relate this function to the corresponding function on the universal cover. And if you do the computations and sort of compute the curvature tensor, etc., you see that this function Q composed with the map is equal to the square of the second derivatives of this function H. And this means that these second derivatives are bounded. Okay, so this is something that would not happen of course, for a general standard PP wave, only because it is a lift of a compact PP wave. Okay, so this was sort of a bit technical to prove, but it's, yeah, so I think it's worth seeing how this goes. And so let's look at some applications. So the first application is to what Miguel Sanchez also refers to as the Elast Kun problem. And I just looked at the book by Elast and Kun, and they really have it as a problem there. They even give some hint how to solve it, which I didn't use. I mean, we get this result as a consequence of our result. So let me remind you what a plane wave is. So a plane wave is a PP wave that satisfies an additional curvature condition. So curvature is even more special, namely that if you take the covariant derivative of the curvature tensor in direction of V perp, it is 0. So the curvature tensor only changes transversal to these codimension 1 leaves. And this is equivalent to this function H being just a quadratic polynomial with coefficients depending on U. So this is this equation here, right? So, and then this problem that Elast and Kun put in their book is prove that complete Ritchie-flat PP waves are plane waves, no matter which topology one chooses. And I guess this is almost a quote, but the second part of the sentence is an exact quote. So they just put it, no matter which topology one chooses, which is a bit ambiguous, I guess. But so we have just chosen the topology to be a compact manifold, which probably wasn't in their what they had in mind. But if you choose the PP wave to be compact and Ritchie-flat, then it is a plane wave, right? And we are not assuming any completeness here. Well, it follows from the fact that it's a compact PP wave, but if you add the condition Ritchie-flat, it must be a plane wave. And this just follows from what we've just seen about the boundedness of this function. So the metric GH, which is the covering metric, is harmonic. If it's Ritchie-flat, it's harmonic, but it's also bounded. This is what we've just seen. So then you can just use the maximum principle to show that, to obtain that this must be a constant function. So the second derivative are a constant function with respect to the xi's. So you get exactly that it's a quadratic polynomial in the xi's. And this means that it's a plane wave. So this is one application. So the other one is about these indecomposable Lorentzian spaces, symmetric spaces, locally symmetric spaces. So let me just briefly explain what I mean by indecomposable and decomposable. So we say that a semi-Riemannian manifold is decomposable if it is locally isometric to a semi-Riemannian product metric. So the metric is locally isometric to a product metric. And this is equivalent to the holonomy group having a non-degenerate invariant subspace. And indecomposable if it's not decomposable. So then, if you look in the Riemannian setting, indecomposable is the same as irreducible. And then you would, if you look at symmetric spaces, you would just get the classification of irreducible Riemannian spaces. So here, in Lorentzian signature, indecomposable is not the same as irreducible. It's a weaker condition. And Kahn and Ballach have shown that there are 2 types of indecomposable Lorentzian symmetric spaces. There are the spaces of constant sectional curvature, obviously, And then there are these Kahn-Wallach spaces, and that's it. So there's no long list like in the Riemannian setting. However, the Kahn-Wallach space are not irreducible. They do have a parallel null vector field. Okay, so what are these Kahn-Wallach spaces? So they are just a very, locally, they're just a very specific PP wave metric where this function h is just a quadratic polynomial with constant coefficients. So each Kahn-Wallach space is given by a matrix as a symmetric matrix. Well, essentially it's given by the eigenvalues of this matrix, but let's just write it like this. And so these spaces have a solvable transvection group, which which is the oscillator group, which I think Charles yesterday called it the twisted Heisenberg. So it's so you take a derivation of the Heisenberg group, and the derivation is defined by this matrix S, and this gives you the oscillator. And that's the transvection group. The isometry group can be bigger, so you could have a compact factor in the isometry, but in the smaller transvection group is just given as the oscillator. And so then they are quotient of the oscillator by Rn, and their holonomy is equal to Rn. Okay, so, but locally there are PP waves. And so we obtain this result that a compact Lorentzian manifold that is locally isometric to a Kahn-Wallach space is complete. And the problem, of course, I said they are locally PP waves. The problem, of course, is that they may not have a global parallel null vector field because we are only making a local assumption on the geometry. So this means the elements of the holonomy group are of this following form. So here the first column corresponds to the invariant null line. And if this A would be just 1, then it would have a parallel null vector field. Otherwise, this null vector field can be scaled by the holonomy. And so the first and the second column correspond to V perp. So A is an n by n matrix from On. So now for a symmetric space, the curvature tensor is invariant under the holonomy. So you just apply the holonomy to the curvature tensor and it fixes it. And if you compute the curvature and let this matrix act on it, you will see that this implies this relation. So the matrix S is equal to A times A transposed SA. And if you, for example, take the determinant of S, or of both sides, you will get that A square has to be 1. Yeah, so S is assumed to be non-degenerate for these indecomposable spaces. So this means, so if A is equal to +1, we are good. If it's equal to -1, we just go to the time-orientable cover, get a parallel null vector field, and hence we have a compact PP wave. So these locally Kahn-Wallach spaces are compact PP waves and hence are complete. So this is sort of brings us back to this one entry in the table at the very beginning, where we have now shown that these compact local Kahn-Wallach spaces are complete, and they are given by a quotient of of the globally symmetric space by a lattice of the oscillator group. Okay, so this is what I just said. So you get this corollary from this, that any compact locally symmetric indecomposable Lorentzian manifold is a quotient of either odd dimensional anti-de Sitter space or of a Kahn-Wallach space. And you just can put this proof together from the literature. So constant curvature, there's de Sitter and anti-de Sitter. And then Calabi and Marcus and Kulkarni have shown that neither de Sitter spaces nor even dimensional anti-de Sitter spaces have compact quotients. So this is, you're left with odd dimensional anti-de Sitter and Kahn-Wallach. And as I said, these lattices or these compact quotients of Kahn-Wallach spaces have been studied by Carter and Ulbrich in a paper that is just published in the memoirs of the AMS. So, and of course, after that, we were conjecturing, I guess it's a very optimistic conjecture, that compact locally symmetric Lorentzian manifolds are complete. And at first glance, you might think this is perhaps an easy question because they are locally given as products of these sort of building blocks, but these are only local products, and the local situation doesn't help much when you want to prove completeness. However, the student of mine that I mentioned, so we made some tiny progress here, that if the locally symmetric space is locally isometric to a flat space times the Kahnweiler space, so you allow for sort of two very specific quotients, then our method can be generalized and you get that they are complete. Yeah. But in general, the question is open, and yeah, I would like to answer that. Okay, so this is one open question in terms of locally symmetric compact Lorentzian manifolds. So what I'm dropping in the conjecture is the assumption of indecomposability, right? So that's kind of the point here. And so then my last slide is about further generalization. So the idea really is to show that Lorentzian manifolds with special holonomy are complete if they are compact. Yeah, so by special holonomy, I just mean that the manifold is indecomposable. So I can't split it up into building blocks, but it doesn't have full holonomy. So that's why it's special. So it's a subgroup of the orthogonal group. And there's a fundamental difference to the Riemannian case because SO1 n+1 doesn't have any irreducible subgroups. So this means as soon as you assume that you are in a subgroup of SO, you already have some invariant object, namely you have an invariant null line, and the holonomy is contained in the stabilizer of this null line. So whereas in the Riemannian you have a bunch of irreducible subgroups, which, for example, constitute the list of holonomy groups, Berger's list, but also the list of irreducible symmetric spaces. Here the situation is completely different. It's kind of simpler in some sense because the list is shorter, but also more complicated because the geometry is more degenerate in some sense. Okay, so in the case of special holonomy, you can already assume that you have an invariant null line, parallel null line. So then these counterexamples to completeness of compact manifolds that exist in the literature, for example, the Clifton-Pohl torus and generalizations, they do have a parallel null line, but not a parallel null vector field. So this means if you want to prove some generalization, you have to assume the parallel null vector field, not just the parallel null line. So that's one assumption you have to make, otherwise the conjecture is wrong. So what's the conjecture now? A compact Lorentzian manifold with parallel null vector field is compact. So that's a question that I'm trying to answer. And well, there is kind of, there's slow work in progress, let's put it this way, about which at some point we thought we have a proof, but then we forgot some assumptions and there's still a few gaps. So I guess it's not really a proof what we have. And then I haven't thought about it for a while. So I think this talk is also for me to getting a little bit back into this problem and trying to get into action again to maybe solve this question. So, or also if someone finds a counterexample, that would also be interesting, of course, right? So yeah, so I think this is where I should stop. So, and thank you very much for your attention, and I hope you're all still there.